Hello, and welcome back to our course Computer Communications. Today we continue our journey into the functionality of the network layer. In this recording, we will consider the inside parts of the router and we'll cover the functionality of datagram fragmentation. Alright, let us talk now about what is inside a router. Remember its two key functions: to run routing protocols to determine a path between two end systems throughout the network, and to actually forward datagram from a specific input port to a particular output port. Let us now go through the functionality of all these elements: input ports, switching fabric, and the output ports. Here is a simplified schematic of an input port of a router. So we have a line termination, so we connect a cable here, physical layer. So then we have a link layer which takes care of checking possible errors. And then we have a network layer functionality, including looking up the destination address, taking forwarding decision, and possibly queuing the packets. The role of a switching fabric inside a router is to take packets from an input buffer and to bring them as quickly as possible to an appropriate output buffer. The switching rate is one of the most critical characteristics limiting the overall network performance. Ideally, the switching rate of a switching fabric should be equal to the accumulate rate from all the input lines of a router. So if we have n inputs, for example, then we would desire that the switching rate of the switching fabric would be n times the line rate. There are three types of switching fabrics that currently in use in the routers. The first type is memory switched fabrics. Second type is switching through a bus. And the third type of switching fabrics is crossbar switch. The first generation of routers implemented switching via memory. This is apparently the slowest possible switching technique, because you need to copy the packet into the memory, into the common memory first, and then you need to read this packet, essentially copy it again, and transfer via system bus to the appropriate output port, as it is illustrated by this animation over here. So we first copy the packets into the memory, and then we read these packets from the memory to the output buffer. Most of the modern routers implement one of the other two techniques. Either they implement switching by a bus, or especially faster routers, the core routers, they implement a crossbar switch. The principle behind switching via bus is rather simple. So we have a common bus, as it is illustrated here, which bandwidth is higher than the bandwidth of the input ports. And then datagrams from a particular input port memory are copied into a particular output port memory. So there is one copy procedure via this shared bus. One of the performance limitations of the bus switching technique is its limitation. It is the contention that happens between different input ports for the bandwidth of the shared bus. In order to overcome these limitations, these performance limitations, a technique called crossbar switch was developed, Essentially, the idea behind crossbar switch is that inside the router you implement a matrix of circuits so that a packet, when being transmitted from one port to a particular output port, does not collide with the packet being transmitted from another input port to another output port. The structure of the output port is a mirror structure of the one for the input port. So basically the datagram after the switching fabric come to the network layer module where they are queued and possibly prioritized for transmission for the output link. So then they are packaged with the link layer, with the link layer structure, link layer frame, and finally sent out to the physical medium. Let's now talk about the buffering component of both the input port and the output port. Actually, it is here when packets can be queued, and it is here where the performance of communications suffer. First, we'll consider queuing inside an input port. The problem that may arise at the input ports is called head-of-the-line blocking. This problem means that queued datagram at the front of the queue prevent other packets in other queues from moving forward. This phenomenon is illustrated on the figures here. On the down left figure, we have two red packets contending for the same output port. So they cannot be transmitted simultaneously. So only one packet will be transmitted. So in our case, let's assume that the packet from the upper input port is transmitted to the output port. So this makes the green packet that is arriving to the input port to be queued inside the network port due to the red packet being pending for transmission. Inside the output port, queuing may happen due to simultaneous arrival due to arrival of packets from different input ports with a rate which exceeds the rate of the output link. In this case, these packets are normally dropped and dropped due to the buffer overflow. Let us talk now about another important functionality of routers, their ability to fragment packets, fragment datagrams. As a matter of fact, different link layer technologies may transfer structures of different sizes. So they have different limits on the size of a unit that can be transferred over a specific link. In this case, we may experience a situation where on the input port we would get a very large datagram, while the output port of a router is connected to a link technology where the maximum allowed size of the transferable unit is less than the one for the input line. In this case, the original datagram should be split into parts and split into parts which fit the MTU of the output link, and then this information will be traveled independently through the network until it will reach the destination host, where these pieces will be reassembled. So the process of splitting a large datagram into a series of smaller ones is called fragmentation. And the reverse process of assembling a larger datagram from a set of smaller datagrams is called reassembly. Once again, it is very important to remember that fragmentation may happen inside the network, while reassembly happens only at the destination hosts. Fragmentation of the incoming datagrams happen in a rather straightforward way. So you need to take the payload of the datagram, you need to split it into smaller pieces, and you need to add to each piece a control information, a network layer header, which also would indicate the position of the piece inside the larger datagram. The fields of the network, the fields of the network layer header that would help us to identify um, a fragment, a position of a fragment within the larger datagram are length, identification, fragmentation flag, and the offset of the piece inside the larger datagram. The length field indicates the length of the payload plus the size of the network layer header. In the case of IP protocol, if we have 1480 bytes inside the payload, then we need to add 20 bytes of the network layer header to which will be recorded in this field. Obviously, the identification field will be the same in all fragments that we get. Fragment flag will be interpreted in this way. As soon as it equals to 1, it means that this packet is just a fragment of a larger one. When the fragment flag is set to 0, it means that this is the last bit of the fragmented packet. Finally, the offset field indicates the position of the payload part inside the larger datagram. And it is important that this field is measured in number of octets, in number of chunks of 8 bytes. If in the payload part of the first fragment we have 1480 bytes of data, it means that the offset for the next fragment would be 1480 bytes divided by 8, which equals to 185. Alright, that's it for now. Next time we continue with the functionality of the Internet protocol. Bye bye.